Okay, this is going to be a review of the circuits lab that we did in class. If you remember, we had a battery pack, switch, some light bulbs, we hooked them all up. We used the multimeters to measure current in various places and the voltage drops. So one thing, this lab, you may not have learned anything from this lab because we knew all the circuit rules before we headed back there and did it, in terms of the junction rule and loop rule and things like that. So that should have all agreed with what we learned in the front of the classroom. So anyway, this the answer key I have here might be a slightly different version than what you guys actually did, but the major content is going to be the same. So the first thing, we connected two light bulbs up in series and we measured the current in various places. So in my answer key I've got I1, I2, I3, I4, and that's in these locations. Again, for current, we have to take the this wire out of it and we replaced it with the meter. The ammeter has to have current running through it to measure the current. So you should have gotten roughly the same current all the way around. I'm saying 0.2 amps because that's about what you guys should have gotten. And that is true everywhere. This question here, when you open the switch, it breaks the circuit, so none of the light bulbs will light up because no current is running through it. When you close that switch, that allows the current to flow through it, and then the light bulbs light up. The current each wire, conclusion about the... Okay, so the current through each bulb is going to be 0.2 amps. You guys know in series, the current is the same everywhere. It does not get used up, contrary to what some people believe. Current in series is constant. Okay, so then we're going to look at voltage across different elements. So the voltage drop is what I've been calling that in class. So voltmeter must be connected in parallel. So if you remember, you kept the circuit completely intact and you just took the leads of the meter and put them like on point G and F, for example, to get the voltage drop across there. Did not disconnect anything. We wanted the voltage across those elements, so that we connected the voltmeter in parallel. Okay, so again, numbers, these are about what you should have gotten. So a standard battery, whether it's a D or a C or a AA or a AAA, those are labeled at 1.5 volts. Fresh out of the package, they're a little bit more than that. But then as you use them, that decreases. We had two batteries, so the voltage should have been around 3 volts. You may have gotten a little less than that. But anyway, excuse me. Voltage HA, and that's across the battery. So that's the battery voltage, 3 volts. And then I had to measure, across the wires. So AB, you should have gotten pretty much 0 there. You might have gotten a very small number. Remember, everything in a circuit has some sort of resistance. Now, a wire has very little resistance compared to, say, a light bulb. So the voltage drop across a wire should be pretty small compared to the light bulb. And that's why, I wrote 0 in these, because you should have gotten pretty close to 0. Remember, a volt is energy per charge. It's joules per coulomb. So as you go through something with no resistance, you're not going to lose any of that energy per coulomb of charge. When you go through an element that has resistance, say a light bulb, that's where you're going to lose some energy per charge. And remember, that's joules per coulomb, which is a volt. Okay, so across the wires, and then DE across a light bulb, you should have gotten around 1.5 volts. Across the other light bulb, you should have also gotten around 1.5 volts. Because remember the loop rule, if we start with 3 volts, we have to lose all 3 volts by the time we come back to the battery. So the significant sources where we have a voltage drop, the two light bulbs would share that equally, because in this case, they're identical light bulbs, so it should be split evenly there. Okay, so that's what we're talking about there. Okay, so that's all. Talked about that. Okay, so here compare the voltage supplied by the battery to the voltage across the bulbs. They should be the same. Voltage of the battery is the sum of all the voltage drops across the bulbs. Okay, so now let's go to the parallel. Okay, so I have currents labeled in here. This is about what you should have gotten. Notice that before we had 0.2 amps, when they were in series, now when we connect them in parallel, that went up quite a bit because we're giving those charges more pathways to take. So if you remember my gym analogy, more doors out of the gym meant people can get out of that gym faster, more quickly. Similar with charges flowing through a circuit. The more pathways we have, the bigger that current's going to get. Okay, so anyway, the junction rule here is going to apply. We measured this is about 0.6 amps. This was about 0.3. This is about 0.3. Junction rule states the current going into a junction has to equal the current leaving that junction. So you should have seen that with your numbers in the lab. And then down here, there's another junction. So the current going into this junction, 0.3 and 0.3, should equal the current leaving that junction, 0.6. Okay, so that's really the big thing. I'm not going to really dwell on these numbers down here because it's basically what I just talked about. Oh, by the way, you measured the current here through wire 2. You measured the current through wire 5. That should be the same. No different because there's no junction in here. That current should all be the same throughout that. Same thing with wires 3 and 4 and wires 6 and 1. Okay, so then number 9, the general statement is Kirchhoff's junction rule. The current going into a junction equals the current leaving that junction. Okay, voltage across elements in parallel. Okay, so this, if we look at a single loop, if we take a loop right in here, we have 3 volts from the battery. We have to lose all 3 volts by the time we get back. So when you measure this, it's about 3 volts now. If you remember when they were in series, each light bulb was about 1.5 volts. They added up to 3 because all the current was going through both bulbs. In this case, some charges only go through one bulb, so they have to lose all 3 volts in that bulb. Similar with this outer loop. Okay, the charges going through this outer loop have to end up at 0 when they get back, so they're losing all 3 volts in that the bulb they go through. Okay, so a lot of zeros in here. I had you guys measure voltage drop, from like A to B. There is no drop there. Okay, if the charges are leaving the battery and they have 3 volts, in other words 3 joules per coulomb, they still have 3 joules per coulomb here. They haven't lost any of that yet. In fact, even when they get to point C, they still have 3 joules per coulomb. So when you check the voltage drop or the potential difference between A and C, it should be 0. Okay, it's not until you go across a resistor or a light bulb in this case that you're going to get a potential difference. Okay, so now at D, these charges have gone through the light bulb. Now they're down to 0 joules per coulomb or 0 volts. So if we look at the potential difference across A to D, we will get a value of 3 volts there, or -3 depending on how you look at that. Similar with like A to G, that potential difference should be 0 because the charges taking this path, they're still at 3 volts when they get here. Now they're losing the 3 volts, now they're down to 0. So if we look A to H, we should see a potential difference of 3 or -3 volts there. Okay, so that's why this table has a bunch of zeros in there. Again, that V is a potential difference, the difference between those 2 points. Okay, so now I asked you to put a switch between points A and B. Okay, so like right in here. So if you open that switch, that's going to break the current through here, which is going to break the current everywhere in the circuit. When you close that switch, the light bulbs will be on. Also, did you notice that, if you remember this, the brightness of these bulbs was about the same? Okay, now when they were in series, the first part, they were significantly dimmer. Well, that's because you have less current going through them. The brightness is actually related to power. We don't really need to worry about that. We can look at the current for that for our purposes. Okay, so now put the switch between B and G. So if I put the switch here and I open it, well, that's only cutting off the current in this branch. The current can still go through this first light bulb. So if I open the switch here, this light bulb should go off. This one stays on the same brightness. Okay, the same brightness because we still have a drop of 3 volts here. That current is not affected. The only thing that an open switch here does is it will turn that light bulb off. Okay, and then the other thing, with the switch closed, so basically how we have it seen here, if you unscrew a light bulb, well, unscrewing a light bulb, or let's just say one light bulb burns out, that's going to break the current going through this branch, but you still have current going through this outer branch, so that light bulb would still stay on. Okay, same thing if this light bulb burned out, you would still have current going through this inner branch, so that light bulb would stay on. So then my last question is, houses have several circuits in them, typically for different areas. You have a breaker box probably in your basement. Maybe I'll go look at ours. And you'll notice that it's labeled for different rooms in the house: kitchen, bathrooms, living room, and so on. Well, each of those are separate circuits, and they are wired in parallel. The idea is when you turn, let's say in your bedroom, when you turn the light switch off, well, do you want your alarm clock to go off too? No. Okay, so think about a parallel circuit. The light switch is on one branch of that parallel circuit. Your alarm clock is on, say, another. Same things with appliances in the kitchen. If you turn the blender off, you don't want the microwave to shut off at the same time. So those are on parallel circuits. Okay, so let's take a walk here. All right, so that's really it for the circuit lab. Like I said, it is exactly like the circuits we've been doing in class at the front of the classroom. So hopefully you saw the relationship there. Okay, so here I'm going to try to show you our circuit breaker. Right there it is. Okay, so that's what it looks like. If you overload one of the circuits, let's say if you have too many things plugged into a parallel circuit, that total current goes up because you've given the charges more pathways to go through. So when that total current goes up, it could cause a danger. The wires are only meant to handle so much current. So then you see the black switches there on the left. I'll try to point at them over here. Okay, those are the different circuits. So a lot of times if you overload a circuit, it breaks that circuit. This is a safety feature, and then you have to go downstairs and reset that circuit. But that's really the main thing for the power box like this. Every house has one. It might look a little bit different. You might have more or less switches on there, but it all works the same. It's again a safety feature. Okay, so that's really it. As always, if you have any questions, shoot me an email. Otherwise, keep looking at those circuits. Look at the other circuit videos to get a review on how to solve the circuits, solving for current and voltage drops across various components in that circuit. Okay, that's it.